we talked about two things that seem a little different, right? The last 2 days. So we talked about inverse functions, and then now we're talking about composite functions. Why are they in the same section? How do they relate? It's a mystery. No, it's not a mystery, because when you compose inverse functions, something useful happens. So here's the big note. This is the really big result of this section, you guys. Note, for inverse functions, f and f inverse, it turns out that if you compose them, if you take f of f inverse of x, like that, which is really the same as f circle f inverse, right? Of x. If you compose those two functions, they knock each other out, and you just get x. And it works the other way around, by the way. If you make the f inverse the outside function, f inverse of f of x is also equal to x, which, by the way, using the composite notation is f inverse circle f of x. Long story short, you compose inverse functions, they knock each other out, and you're just left with x. Now, why is that useful? Well, you've been using this idea all along. What happens if you want to solve an equation like x squared equals 9? What do you do to both sides? You don't square both sides, you square root both sides. And let's, for the sake of argument, let's suppose we're looking for the positive root. You square root both sides. Find x greater than 0, to keep it simple. And you get x equals 3 when you're looking for the positive root, like if it's the side, like if x represents the side of a triangle or something, or a square or something. So x equals 3, right? Well, what did you really do? There's a function called the square root function. So f of x equals the square root of x would be there's lots of different root functions, but this would be the square root function. There's something called the squaring function. We'll call it g for the sake of argument. The squaring function takes the input, if you call it x, and it squares it. And it turns out that f and g are inverses of each other. The squaring function is the inverse of the square root function and vice versa. So really what you did was you inserted both sides of the equation. So let me remind you what we started with. We started with x squared equals 9, right? Really what you did was you inserted both sides of this equation into the square root function, which is the inverse of the squaring function. And you guys kind of knew that already, right? You take the square root of something squared, you just get that base x back again, don't you, in this case? So you've been using the idea of inverse functions and you didn't know it. And this idea carries over to many other types of equations. And so the moral of the story is you can use inverse functions to help you solve equations. Solving equations help you solve many, many, many different applications that are very useful. If you're asked to use function composition to show that f of x is equal to x plus 6 divided by 3, and g of x is equal to 3x minus 6, if you're asked to use composition to show that those are inverses, then you don't use that recipe from above to find the inverse. All you do is compose them both ways and show that you get x both times. In other words, you use that property we just stated above. So we want to compose f and g and show that what happens? Well, we want to show that when we this is getting a little busy here, so look inside the red box here. For inverse functions, and only for inverse functions, it's true that f of f inverse of x is equal to x, and f inverse of f of x is equal to x. This is the big property. Big property, true for only inverse functions. So you're not going to be able to find any old f and g that aren't inverses and have this be true. Okay, you're not going to be able to compose any old f and g and get x to pop back out again, at least not going in both directions. So we have f, we have g. We're going to take f of g of x, and we're going to show that we get x. I'm not going to try and fool you. If I tell you to show that they're inverses, they're going to be inverses. So think about it. Work from the inside out. What could I replace g of x with? This is g of x, so I'm going to replace g of x with its output formula. So we get f of g of x is the same as f of 3x minus 6. I'm going to work downward now. And then what do I do with 3x minus 6? It's f of 3x minus 6, so I plug it in right there where the x was in the output formula for f. So what do I get? I get, okay, you could put in a set of parentheses where the x was, then plus 6 divided by 3, and then throw in the 3x minus 6 as the new input. And what's going to happen? On top, you could drop the parentheses. They're not doing anything. What's 3x minus 6 plus 6? So you get 3x over 3, which is x. Big old check mark. That worked. To be sure, you have to go both ways. You have to also find g of f of x. G of f of x, okay, work it from the inside out. What is f of x really equal to? So it's g of x plus 6 over 3. G of f of x is g of x plus 6 over 3 because the output formula for f of x is x plus 6 over 3. And now it's just function notation. But now you're plugging in the new input, this guy, in for the old input in g. So you could rewrite g as 3 times parentheses minus 6, and your new input is x plus 6 over 3. What happens to the 3's? There you go. Okay, this operation outside is multiplication, so you can do this cancellation, right? And you're left with x plus 6 minus 6, which is x. Big old check mark there. And you could say, oh, you want to use a snobby sounding word? Thus, henceforth, how about behold? That's a pretty good one. Now we'll stick with thus. Thus, f and g are inverses. Because function composition in both directions give you x, you can say that they are in fact inverses of each other.